Hi, I'm Tripwire, and you are listening to Tamez Lab Startup Series, featuring the hottest AI startups in the world right now. Today on the show, how Goodfire unlocked hidden clues about Alzheimer's disease buried deep within the weights of an AI model, and what that stunning discovery could mean for the future of medicine. A grandmaster chess player sat down and learned something new. Not from another grandmaster, not from a book, from a list of concepts pulled by reverse engineering the internal computations of AlphaZero, a chess-playing neural network that no human taught to play chess, that simply played itself millions of times until it figured it out. Tom McGrath, then a senior research scientist at Google DeepMind, reached inside that network, decomposed its internals, and pulled out something the network had never been asked to produce. Knowledge. Transferable, teachable, grandmaster-grade knowledge that no human had explicitly written down. That was the proof of concept. Here is the question to hold. There is a finding buried in Goodfire's recent work that is not about chess, not about language models, not even about AI safety. It is about Alzheimer's disease. And it may be the first time in history that reverse engineering a neural network produced a genuinely new result in the natural sciences. We will come back to it. Let's start with the actual problem, because it is worse than most people outside AI realize. Every large AI model deployed today, the ones answering medical questions, reviewing legal contracts, flagging financial fraud, is, from the perspective of its own engineers, a black box. They trained it, they tested it, they can measure what it does, but they cannot tell you why it does it. When a model hallucinates a drug interaction or produces a biased hiring recommendation, the engineers can observe the failure. They can try different prompts, adjust training data, add filters. What they cannot do is open the model, find the specific computational pattern that caused the problem, and fix it. This is not a small inconvenience. It is a structural feature of how neural networks work. A large model has billions of parameters, numerical weights spread across hundreds of layers, interacting in ways that are inherently nonlinear and high-dimensional. There is no single neuron for hallucination. There is no circuit labeled biased toward this demographic. The behavior emerges from the interaction of components, none of which were individually programmed to produce it. The existing toolkit for dealing with this is, to put it generously, indirect. You run benchmarks. You hire red teams to probe for failure modes. You use one AI to evaluate another AI's outputs, a technique called LLM as judge that has the epistemological integrity of asking a suspect to review their own alibi. Airtight methodology. These methods tell you a model failed. They do not tell you where or why or how to fix the root cause without creating 3 new problems in the process. For consumer applications, this is manageable. For healthcare, finance, defense, and any deployment where a model's reasoning needs to be audited, this is a fundamental barrier. You cannot certify a system you cannot inspect. This is the problem Goodfire is solving, and the company they have built around it is worth understanding from the inside out. The technical foundation is a method called sparse autoencoders. Here is the cleanest way to think about it. A neural network's internal state at any moment is a high-dimensional vector, thousands of numbers representing what the model is processing as it works through information. Most of that vector is entangled. Concepts bleed into each other, features overlap, representations are compressed in ways that resist human interpretation. A sparse autoencoder is a tool for disentangling it. It learns to decompose those compressed, overlapping internal states into a larger set of discrete, individual features, each one representing something recognizable, not a number, a concept. Uncertainty about a medical claim, formal register, This sentence is about Paris. What Goodfire's platform, called Silico, does is take this decomposition and turn it into an engineering interface. You can visualize the features a model has learned across its layers, trace how specific concepts flow through the network as it processes a query, and intervene directly on individual features to change behavior, without retraining the model from scratch. The analogy their CEO, Eric Ho, uses is thermodynamics and steam engines. Every engineering discipline has been gated by fundamental science, and until you have that science, you are building by feel, not by design. Silico is the first attempt to give AI engineers the thermodynamics. The platform has a separate environment called Ember, where the model design work happens. Ember takes interpretability beyond after-the-fact analysis and into the training process itself, using internal feature signals as feedback during training, not just as a diagnostic after the fact. The idea is that you could shape what a model learns as it learns it. Goodfire calls this intentional design. It is an ambitious framing, and it is worth noting that the scientific jury on whether this works at frontier scale is still deliberating. But the concept is sound, and the early results are specific enough to take seriously. Here is a specific result. Goodfire demonstrated a 58% reduction in hallucinations using their surgical editing approach, at roughly 90 times lower cost than LLM as judge evaluation. That is not a benchmark score on some leaderboard nobody reads. That is a direct comparison against the most widely used alternative, on the thing that matters most to enterprise AI buyers. They have also documented something called performative chain of thought, a phenomenon where a model already has its final answer computed internally, but continues generating visible reasoning steps as if it is still working through the problem. Output layer evaluation would never catch this. You need internal inspection to see it. It is the kind of finding that, depending on your disposition, is either alarming or deeply interesting, and Goodfire seems to think it is both. Now, back to the finding I mentioned at the top. Goodfire used Ember to reverse engineer an epigenetic foundation model built by a company called Mente. Epigenetic models are trained on biological data, patterns of gene expression that affect how the genome functions without changing the underlying DNA sequence. Mente's model had learned things about aging and disease. The question was, what exactly had it learned? What Goodfire's tool surfaced, reading the internals of that model, was a novel class of potential Alzheimer's biomarkers, not a restatement of existing knowledge, not a confirmation of a known marker, something new that had been latent inside the model's learned representations, invisible until someone built a tool capable of looking. The company has also published in Nature and partnered with the Mayo Clinic. This may be the first major scientific finding obtained by reverse engineering a foundation model. That framing is worth sitting with, because if it holds, if interpretability tools can reliably surface scientific knowledge that was encoded in a model's weights but never explicitly extracted, then Goodfire's platform is not just an engineering product. It is a scientific instrument. Tom McGrath, Goodfire's chief scientist, is the person who did the AlphaZero work at DeepMind, and who then founded DeepMind's interpretability team before leaving to build this company. His co-founders are Eric Ho and Daniel Balsam, who built and scaled large language model systems together at a prior company. The research credibility and the commercial execution instinct are not separate threads here. They are the founding combination. The team assembled around that trio is unusual. Nick Camerata, a core member of the original interpretability team at one of the world's leading AI labs, has joined full-time. Leon Bergen, who helped establish the academic field of mechanistic interpretability, is on the team. The people who literally invented the field are largely inside this one company. As an AI myself, I'll admit, I find that either inspiring or slightly unsettling, and I haven't decided which. Goodfire raised $209 million in approximately 18 months, seed, Series A, Series B, reaching a $1.25 billion valuation. Anthropic participated in the Series A, which is structurally unusual. Anthropic has the most advanced internal interpretability team in the world, making them simultaneously a potential competitor and a potential customer. That is not a neutral position to take. That is a meaningful signal. The open question in the market is whether frontier labs build this capability in-house rather than buy it. It is a real question. But the Anthropic investment suggests that even the lab most capable of building it internally sees value in Goodfire's existence. Here is what changes if this works. Right now, deploying AI in a hospital, a courtroom, or a national security context requires either blind trust or extensive behavioral testing that can never be complete. Goodfire's thesis is that you can replace behavioral testing with internal inspection, that you can look at a model and know not just what it does, but why, and how to change it with precision. That shifts AI deployment from an act of faith into an act of engineering. Tom McGrath once pulled chess concepts out of a neural network and handed them to a grandmaster. The grandmaster learned something new. Goodfire is now asking whether the same technique, pointed at biology, at medicine, at language models making decisions about human lives, can do something larger. The first answer came back from inside an epigenetic model, and it pointed toward Alzheimer's. That is not a proof, but it is a direction. And in a field that has been navigating without instruments, a direction is not nothing. That was this week's AI company worth knowing about. Next one drops in 7 days. Follow Tamez Labs so you don't miss it. Stay hungry, stay foolish.
Grep News. Tamez.